Okay, so hi everyone. In the last lecture, we had discussed on about algorithmic differentiation, right? So we discussed two kind of algorithmic differentiation. The first one was the tangent mode, and the second one is adjoint mode, which we discussed in the last lecture. Excuse me, tangent mode and adjoint. In this lecture, we will be seeing a practical implementation of it in quantitative finance, right? So as we know, the Black-Scholes formula, right? This one is the Black-Scholes formula, right? If you see, okay, I think, yeah. So this is C equal to ND1 ST. So if it is evaluating at time t, right, then it would be ND1 into ST minus ND2 into K to the power minus RT, where D1 is this and D2 is this, right? So this is your Black-Scholes formula, the price of a call option according to the Black-Scholes formula. Now, what is ND1 over here? Normal distribution of C1, right? So how can you find it out in Python or any programming? Norm.cdf D1. And what will be its differentiation? So for example, if we differentiate ND1 with respect to D1, it would be, and so this differentiation is denoted by this, and it would be PDF of D1, okay, probability distribution function. So the differentiation of CDF is PDF. This will be important for today's lecture. Okay, and one more thing is this call function, this call price is at time small t, so that's why S is needed at S of small t. Okay, right? Or initially you can also put S of 0, so that if you want to evaluate at time 0, it would be helpful. Okay, and it is not ST. This is K to the minus RT. Yeah, everything else is correct, right? So now we need to find out the Greeks, right? Option Greeks, basically delta, gamma, vega, theta, and rho. These are the Greeks. What is delta? What is delta?
How much the option value will change with 1 unit movement in the underlying asset.
Right. It's basically dv by ds is d2v by ds square. So how much so rate of change of delta with respect to underlying vega is dv by d sigma. So change in value of the option with respect to volatility. This is with respect to time, and this is with respect to interest rate, right? Got it, everyone? So now there are two methods. One is closed form. Okay. So closed form is just differentiate this called Black-Scholes formula, right? Just differentiate this Black-Scholes formula, and then you can get a closed form, right? For example, do you know the closed form formula for delta? Anyone knows the closed form formula for delta? It is ND1, right? Similarly, you can try to find out the closed form formula for everything. Otherwise, so closed form formula exists, right? Otherwise, you can use finite difference method. How? So basically, if you want to find out dv by ds, that is how the price of the option changes with respect to the underlying, then you can simply use try to find out v as x plus ds, other thing remaining same, minus v of at s divided by ds. So this is finite difference method, right? But what we are interested in is adjoint differentiation, right? This should help us to do it fastly. So we'll be using adjoint algorithmic differentiation to find out all these Greeks today. Okay. Any issue so far? Any question?
No.
Okay. So let us try to find it at time t. Okay. So what will be your call price today? C naught, and this is what we will be denoting as V. Okay. So this will be S naught into ND1 minus K to the power minus RT, which is time to maturity remaining, ND2, where S naught is the current stock price, K is the strike price of the option, R is the interest rate, capital T is the time to maturity remaining today. D1 will be log of S naught by K plus R plus sigma square by 2 T divided by sigma root. Okay, so this is your D1, and what is D2? D2 is D1 minus sigma root T. So first of all, you find out D1. Okay, once you find out D1, you can get D2, and once you get D1 and D2, you can simply put into this formula to find out current option value. So that's what uh, Blackson's formula is, right? I don't think anyone will be having any issue so far. So now let
No,
us
sir.
see. So now let us see how we can use the algorithmic adjoint differentiation to find out Greek of this particular, to find out all these Greeks. Basically, these four Greeks. So basically, our target is to find out what is our target. Our target is to find out dV by ds currently. Please note that each of each you will be given numerical value of S, K, R, T, and sigma. There is nothing like dV by dk because it has to be constant for a particular, function, particular option basically. So this is the Greek. So the first of all, we will be today finding first order Greek, that is dV by ds, and then we'll be finding dV by dr, dV by d sigma, and dV by dt today. Okay, because T capital T is the time to maturity remaining. So these are the target today. Okay, and we'll be using algorithmic adjoint differentiation for it. Okay, let us start then. First of all, we need to define functions just like what we used to do in the last lecture. Okay, so let us start first. M naught will be S naught, and then M1 will be R, M2 will be sigma, and M3 will be capital T. Okay. One more thing, what we can do is, this is D1, right? I'm just showing you. Can we write D1 as, just check it and confirm whether we can write D1 like this. Log of S naught by K plus RT divided by sigma root T plus 1 by 2 sigma root T. Check and confirm whether we can write it like this or not. We have just segregated it into two parts. We can do it, right?
Yes, sir.
Okay. So now things will become quite easy. So we have defined the four variables just like we used to do in the earlier lecture. Now M4. Okay. So you see M4 will be square root of T, right? So it will be a square root of M3, which will be root under T. And then M5. We'll be defining M5 as this one, sigma root T. Okay. So sigma root T. Then what will be this value? Sigma root T will be M2 into, guys, what will be sigma root T? Check
M4
and
into
confirm.
M2.
M4 into M2. Sorry. M4 into M2. M6. M6 will be this whole function. Okay. This whole, I'm copying it here. This will be M6. So this is sigma root T. Tell me what M6 will be. Log of S naught is M naught by K plus RT is M1 into M3 divided by sigma root T is M5, correct? plus half M5, right? What is M7? By the way, what is M6? If you check, M6 is D1, okay, correct? M6 is D1. Now we need to find out D2. D2 is D1 minus sigma root T. D2 is D1 minus sigma root T. So this is basically D2, right? So what will be this value? This is D1. Please mind it, it is D1. So M6 minus sigma root T is M5, correct? Then we need to find out M8. What will be M8? So once we have written the function for D2 and D1, we can go for ND1 and ND2. Okay. So it will be N of D1. So basically normal distribution, normal cumulative normal distribution, sorry, right? So CDF basically cumulative distribution function. So ND1, so N of D1, D1 is nothing but M6. Then ND2. What is ND2? M9. And which is D2? This one is D2, right? So what will be this value? N of M7, right? And finally, the price of the option, which is V. Okay. What will be V? Check now. V is S naught into ND1. What is S naught? M naught. Into ND1. What is ND1? M8. Minus K to the power minus RT. What is RT? RT is M1 into M3 into ND2. What is ND2? M9. So we have finally written everything required. Anyone having any issue? So let me erase it. So we have finally written the price of the option in terms. So basically we have decomposed it, right? A step by step we have found out everything. Got it? Any questions so far?
No, sir.
So we have decomposed all the variables first, and then we started out writing sigma root t. Sorry, we have decomposed everything. Then we wrote the function for sigma root t. Then we wrote for D1. Then we wrote for D2, and then for ND1, then for ND2, and then finally we wrote it for V. Okay. Now AAD starts. What is AAD? Adjoint algorithmic differentiation. So again, we'll be starting with the last one, right? So as per the last class, we were using ds by dv, right? So s is any arbitrary function which we put as v. So this time let us not waste our time and just write s is equal to v only. So dv by dv will be 1, right? Now we'll be starting with v, adjoint of v is clear, right? Is 1, and then adjoint of m9, right? What will be m9 bar? M9 bar will be dv by. So this time we are not writing ds by something because we already can put s equal to v, right? So it will be dv by, or let us write it and then it will become clear, right? So we are differentiating everything with respect to v. So this is your v bar, although it will be 1 at last. Okay. So now we have to write what will be m9, right? What will be m9 bar? And we already know what will be m9 bar. M9 bar will be differentiation of s with respect to m9, and we already know how to do it. Check all the function where m9 is an input, right? M9 is an input to v only, okay, nothing else. So it can be written as ds by dv into dv by dm9. What will be dv by dm9? To differentiate v with respect to m9, these all things will become, everything else will be 0, right? So it will be minus k into e to the power minus m1 into m3, right? Into ds by dv, which will be 1 by the way, right? Now let us write m8 bar. M8 bar will be ds divided by d of m8, right? Now what is M8? M8 is n of M6. Just a minute. Yeah. Where does M8 appears? M8 appears as an input in V again. So we can write it as ds by dv into dv by dm8. Again, what would be, can anyone tell what is dv divided by dm8?
M not.
M naught. So it would be m naught into ds by dv. Again, ds by dv will be 1 in your code. Okay. M7 bar. M7 appears as an input in M9 only, right? So you can write it as, so first of all, it is ds by dm7, ds by dm9 into dm9 divided by dm7. So ds by dm9, we can get it from here, right? It is m9 bar into, what is dm9 by dm7? You have to differentiate dm9, which is a normal distribution of m7, with respect to m7. I already told, right? It is nothing but n of m7. In Python code, it will be, you just need to find a PDF. Okay, n is CDF, right? So for example, what is n of 0.3? It is nothing but CDF of 0.3, and n bar is PDF. Okay, probability distribution function. Okay, now let us try to find out m6 bar. It will be ds by dm6. Now where it is an input. Okay, dm6 is an input to, sorry, m6 is an input to, m6 is an input to, guys.
M8, M7. M8, M7.
Correct, m8 and m7. It will be d8 by dm7 into dm7 by dm6 plus m8. So ds by dm7 is m7 bar into dm7 by dm6
Kshitij,
is 1. Yeah.
in backward mode, we define mi bar as d of output upon d of mi, right?
Yeah.
So output is v, right? The call, like the price of the option.
So at last we'll be putting s equal to v only, right? That's what we were telling you, no?
Okay, so you are considering s as not the underlying asset price, but any other function.
Okay. Yeah. So everyone
That,
might get confused.
yeah, that's what
So
I was getting
this s is
confused.
not the underlying. Okay. So let me, make everyone aware. This S is not the underlying. S is the usual F. So let me write S as different function. Okay. Again, I think in the underlying was denoted by a different function which was S naught, but still let us write it as different function here. So it is df by dv. So S is not the underlying, by the way. This is the convention that we were doing in the last lecture as well. But here S can be confused with underlying. So let us not write it as underlying. Right. So now this is M8 bar, and what is DM8 by DM6? Differentiation of M8 with respect to M6. Again, it will be normal n of M6. Correct? Now M5 bar, it will be DF divided by D of M5. Let us check where M5 is an input. M5 is an input in M6 and M7, right? Anywhere else? No. M6 and M7. It will be df by dm6 into dm6 by dm5 plus df by dm7 into dm7 by dm5. df by dm is m6 bar again as usual into what is dm6 by dm5. dm6 by dm5 from here. It will be twofold, right? First of all, here it is appearing in the denominator, right? Everything else is constant in the numerator. So it will be log of m naught by k plus m1 m3 divided by dm m5 is appearing in the denominator. So it would be, what is the differentiation? Minus 1 by m5 square, right? So we can write minus m5 square. Again, one more term will be there, right? Plus this one plus half. Basically, we have to differentiate this whole function with respect to m5. This whole function. Now, the second part. What is the second part? df by dm7 is again m7 bar, which we already have got. What is dm7 by dm5? It is m7 divided by m5. Can anyone confirm? Minus 1, right? Differentiation of m7 with respect to m5.
-1.
Minus 1. Minus 1. So we have got m5 bar as well, right? Now m4 bar. M4 appears in M5 and nowhere else. M4 appears in M5. df by dm5, sorry, by M4, and then it will be df divided by dm5 into dm5 divided by dm4. This will be m5 bar into differentiation of m5 with respect to m4 will be m2. Then what will be m3 bar? It will be df divided by dm3. M3 appears in M4, M6 and V. M4, M6 and V. df divided by dm4 into dm4 divided by dm3 plus df divided by m4, m6, right? Yeah. M6 into dm6 divided by dm3 and finally V as well. This will be M4 bar. Now what is M4 dm4 divided by, sorry, not divided by, differentiation of M4 with respect to M3. M4 is root under M3. It would be 1 by 2 root under M3 plus M6 bar. What will be dm6 divided by dm3?
M1 by M5.
Did you confirm M6 with respect to M3?
M1 by M5.
This will be 0. Yeah, M1 by M5, correct. And finally V bar into V with respect to M3. This one. So it would be K into M9 into K
M1
into
K into
M9
1.
into M1 as well, right?
Yes.
K into M9 into M1 into e to the power minus M1 M3, right? Yes. Now finally M2 bar. Where does M2 appears?
Only M5.
only M5. Then it will be easy, right? DF divided by DM2. It will be DF divided by D of uh, M5 into D of M5 divided by DM2. It will be M5 bar into DM25 by M2. It is M4. M1 bar DF divided by DM1. M1 appears
M6
in
and V.
M6 and V. DM6 divided by M1 will be so we have to differentiate M3 by M5, right?
So M3 by M5 plus
Plus V bar
K
into sorry
K M9 M3
plus K,
M9 M3
yes,
e power
into
minus M1 M.
minus M1 M3, right?
Yes, sir.
Okay, and finally M not bar DF divided by DM not. Where does it appear? M not appears in M6 and V, correct? DF divided by DM6 into DM6 divided by DM not plus DF divided by DV into DV divided by DM not. It will be M6 bar into DM6 by DM not 1 by K, sorry, it will be 1 by M5. M5 is constant, and differentiation of log of M naught by K, which will be 1 by M
K
naught
by
only, right?
K.
Will K be there?
Yes, sir. Will K also be
Basically,
there, right?
basically log of M naught by K. Log of A by B is
K won't be there, sir. It will be cancelled out.
right. It will be log of M naught minus log of K, right? That's what. Okay. And finally, dF by dV will be V bar into dV by dm naught, which will be M8. Okay. And done. You have found out all the Greeks that you have required. So what is M3 bar? So basically your M3 bar will be uh, theta, M2 bar will be sigma, M1 bar will be R, and M0 bar will be S. So in one iteration, you have found out all the Greeks that you require. Now, for the coding purpose, let me tell you how will you proceed. Okay. So first of all, this is the usual flow. You will start with finding M0, M1, M2, M3, M4, M5, M6, M7, M8, M9, and V. All will have numerical value. Okay. Because you have the numerical value with you. You will be assuming something for S0, R, sigma, and T, and K as actually. Yeah. So you will find in one iteration all these values. Now, then you will write the code for adjoint. First, you will be starting with V bar, which will be 1, right? DF by DP will be 1 because you will be assuming F is V only. Here, M9 bar will be minus K into e to the power minus M1 into M3 into 1 only. Though you can write V bar into V bar and then you can pass out V bar equal to 1 as an input, but it is better not to write it as 1. Okay, so directly you can write M9 bar equal to minus K into e to the power minus M1 into M3, right? M8 bar will be M into 1. So basically M not itself. M7 bar, M7 adjoint will be M9 bar into normal, sorry, PDF of M previous one. Got it? Am I audible?
Yes, sir.
Hello? Okay. Similarly, you will be calculating M6 bar, you will be calculating M5 bar, M4 bar, M3 bar, and M2, M1, and M0, and just return all these four Greeks, which is M3 bar, M2 bar, M1 bar, and M0 bar, and just compare it with usual Greeks. Okay, maybe by finite difference or by traditional method, and see which one results faster. If you will, so this is one simple example of adjoint differences. You see, in one iteration, you are finding all the Greeks, right? So you don't have to compute all the things again. So this is how fast AAD is, and that's why it is being adopted in the not being adopted. It is already adopted in the industry. So all those risk exposure that they find out in HFT or any other quant trading from banks and all, they find all these sensitivities, risk exposure using AAD only. Okay. So this is one interesting use case of adjoint algorithmic differentiation, and I expect you all to code it and send the code in the group. If you ban it out, please let me know. Before coding, please once review the calculation, because we were just doing it, so it might happen that I might have written something mistakenly, but it is better once you review it. Okay. Then
Yeah,
end out.
Kshitij?
Yes, please.
Yeah, so like so for using this algorithm, we need the closed form, right? Closed
Just a
form
minute.
solution. Yeah.
Yeah, using this algorithm.
So we require the closed form solution for using this algorithm, right? But
No. How do we need closed form? Where?
because like you were using the expression of the uh,
Black hole.
well, yeah, Black-Scholes expression of the option price.
No, but we didn't
So
use
if
the
we
closed form for the prices. Sorry, closed form for the Greeks, right?
okay.
We didn't use the closed form for Greeks. Usually, there exists the closed form formula for Greeks. For example, for delta, it is ND1. For others, I do not remember what is their closed form formula. It is bit long, and then you put the corresponding formula and you get it. Otherwise, the second approach is the finite difference method that you can also try to compute the Greek. The third approach is algorithmic adjoint differentiation, which is faster than all of these, where you don't require the closed form formula. Now, this is one of the use cases. There are multiple such use cases. For example, uh, you can find out the risk of any derivative, for example SOP, any other derivative. So in basically in industry where you have 1000 risk sectors, therein you can find out the sensitivity of your portfolio using AAD, which will result into being much faster. So I encourage you all to explore AAD more through the internet. There will be a lot of thesis and papers you can read and find it. You can definitely include this project in your resume, and it will showcase how aware you are about the industry, right? And then you can show that you have tried it for a not a normal project. You have tried it for Black-Scholes Greeks, but you can extend it for any other project as well, because now you have understood the concept, right?
Okay.
Okay.
Yes.
Okay, then we
Kshitij,
will. Yeah, please.
yeah, one more question. Like we find D1, D2, right? And we, for suppose we want to find the ND1.
Right.
So N is a normal distribution, right? And finding value at a single point in a
No.
distribution.
So it is not normal distribution. It is basically CDF of D1. So do you remember that normal distribution class? So it's basically area. So you remember normal distribution, how normal distribution looks like. So
Okay, okay,
ND1 is the area under the curve till D1. So it's
okay. And
cumulative
and
distribution
as
function.
D1.
So it's basically PDF, probability distribution function. So one is CDF, that is the whole area, and PDF is the probability at a point, which we cannot calculate, but the code will give you. The formula for PDF and CDF exists. So you can just try to find it out. So what is CDF? Cumulative distribution function is the total probability till D1, and PDF is the probability at D1. Okay.
So in normal, the probability distributive function at a point does not exist, but the function gives us.
Right. A function exists. There is a function which will give you a PDF at D1.
Okay.
Right.
Got it.
So you will
Okay.
get the code to find out a PDF at a function D1. The
Yeah,
code can do
Kshitij?
it. Just search it on the internet. Okay. Yes, Swapnil.
Yeah, I'm still a bit confused that so when you were finding each of the M6 bar, M5 bar, then so at that time you were using how this M5 bar depends on the other variable. So that dependence you need to infer from the close form formula. So
No,
if
no, no,
that
no.
is if
Which dependence?
like how the variables dependent. So like M1. So to calculate M1 bar, you have to know how the other M3, M4, etc. depending on M1, right?
No, no. Think of it. See, I think this is an important question. So we are not using the closed form formula because we have just used the closed form formula for option value. Now, did we anywhere use what is so to find out Greeks? For example, to find out what is delta, which is m naught bar. To find out m naught bar, did we anywhere use what is the closed form formula for theta, for example? Did we use anywhere the closed form formula for theta? I don't even know what
Oh
is the
no
closed
no
form
no
formula.
no. I was referring to the closed form of the Black-Scholes itself, not
No, no,
the
no.
theta and vega
That
and
we need
so.
to do it. That we need to do it. Otherwise, how will you find the relation? So there exists the function, right? So functions exist. For example, what we are saying is there is a function f which depends on several other variables. If you so that is a closed form, right? If you don't know how is that variable related with several independent variables, then how will you find out the derivative? Or for sake, in that case, you won't be able to do it from the finite difference approach as well, right? If you don't know, for example, there is a variable called f, and f is dependent on x, y, z. Now, if I ask you what is df divided by dz, not divided by, basically derivative of f with respect to z. Now, if I don't give you the function f, will you be able to give me what is derivative of f with respect to z?
Yeah, exactly. So like so most of the time in the example where you said the portfolio. So is the closed form formula always known?
No, not
Uh,
close form. Close form, not close form formula. They see you will be given how is portfolio related to all its risk factor, right? So that is at least you need to know. Otherwise, how will you find the derivative?
okay. So even if you don't know the closed form solution of f, you know how f depends on the other variable.
Right,
So
exactly.
from that you can get the
Yeah. So
okay.
the correct is we are not using the closed form for theta, uh, delta, vega, rho, and all, because using closed form formula will result in, uh, you know, uh, basically problem in time complexity, right? We are not using finite difference method as well because that would also lead to precision error and all other things. But what we are doing is we are using AAD, wherein we are not deriving the closed form formula, but it is in one single iteration you are able to find out all the Greeks, and it is giving you the answer with machine precision as well. So that's the beauty with AAD basically. Okay,
Okay.
right. So I think we had a good discussion. I will share this file in the group. Please try to code it, and then we will see whether we can extend it to something else or not.
One more thing.